Hello and welcome to this lecture on decoding of polar codes. Like I mentioned, polar codes are decoded using a sequential decoder. It's also called successive cancellation decoding. The actual version used in practice is maybe a minor modification of what was originally proposed by Larrican, but in spirit it's very true to that. The sequence of operations and how it works, the logic behind it is very similar. Once again, when I describe the decoder, I won't go too much into the theoretical aspects of things. The information theoretic studies is not what we will do. For instance, you will hear this term called Bhattacharya parameter, which is used quite extensively in the design and study of polar decoders. We won't mention that at all. We will focus on implementation as far as these lectures are concerned. Okay. So without further ado, let's get started. So once again, what's the setting of this polar code? I'm repeating this slide from before. You have a block length which is a power of 2. Messages some length is some k which is less than n, and then you form this vector u which has reliability sequence. Okay, and the most reliable positions is where you put your message. All the lesser reliable sequence, first n minus k lesser reliable sequence, you freeze them to 0, and then you do the multiplication u times gn, where gn is this kernel which is 1 0 1 1 tensor product n times. Okay, so this is the basic construction of the polar code. We saw this before. Okay. Now, this slide is also something we have seen before, okay, except for this red part here which says how to realize bit channels in practice. So, the basic idea in polarization is when you combine these bits using that kernel Gn and then you transmit, you create, and then you can split what you have into a set of n bit channels. Okay, each bit going in, each u1 going in, and the output is now different. Okay, the first output for u1 is the entire vector Rn. The first output is the entire vector Rn. For the second bit channel, it's interesting, you have Rn and then you have u1, okay, which is the previous bit. Okay. So, and for the third bit channel, you have Rn and the two previous bits. Okay. Now, how real is it to have the previous bits as included in the output of a channel, because you don't really know what these are, right? These were transmitted at the transmitter end, you don't know what they were. So, is it realistic? That's an important question for us to answer. We will answer that in this lecture. Okay, but this is the construction. But once you do this, it turns out the channels become polarized. Okay, so the quality starts varying. There are very good channels, very bad channels, and you can use them smartly in your decoding or in construction of the code. So that's the crux of the idea behind polar codes. Now the crucial question is what I have here. Okay, how to realize these bit channels in practice? How do you get U1 in practice? Okay, so it's not too difficult to summarize it's not too difficult to think about how you can come up with u1. You can't come up with the exact u1, that's obvious, but you can come up with an estimate for u1. Okay, given Rn and given this first bit channel, can you estimate or decode u1? Okay, however possible you decode. Okay, and remember, in some cases u1 may be frozen. Okay, if u1 is a frozen bit, then you don't need to decode. Okay, if not frozen, can you decode? If it is already frozen, then you know it is 0. Okay, so all these positions, wherever they are frozen, you already know them, these ui's. Okay, you don't have to do any special decoding. But if they are not frozen, then you need to decode. Okay, so that is the idea that is done to realize these bit channels. Let me illustrate that in clearly using a picture like this. Okay, so this picture you have to read sequentially from the top. Okay, so you receive Rn and you do a decode. Okay, and you get a u1 hat. Remember, what is decode? You have to remember this, very important. In decoding, if the bit I is frozen, you don't have to do any special decoding. Okay, if it is frozen, you know the exact ui. Okay, so you set ui hat to be 0. If it is not frozen, you have to do some decoder operations. Okay, what decoder operation you do? In fact, you use a SISO decoder. Okay, even though you don't need the soft output, the decoder uses what the internal decoder that's used here for finding out the estimate is actually a SISO decoder. Okay, so this part is important because the soft output is used later on. Okay, later on when we talk about list decoding, you will see the soft output here is used, but right now in the successive cancellation decoder, we will ignore the soft output, only take the hard output and use it in the next step. Okay, so I haven't told you what this SISO decoder is. I will describe that in the next few slides, but this is essentially the idea to try and recreate the bit channels at the receiver. Okay, how do you recreate the bit channels? Again, you simply decode. Okay, so you decode u1 and then use it here. Okay, and once you have u1 hat, you use Rn and u1 together, and then you decode u2, and so on. You proceed like this. Now, the frozen bits are very important. Okay, so when the bit channel is really not reliable, your decoder will also fail. So that's where the freezing idea comes in. So when you freeze, you know the UI hat for sure. You're not propagating the error too much. Okay, by doing these freezings in frequent places, I mean, as you go from the top to the bottom, once in a while the bit is frozen, right? So when you freeze, you are reinforcing that bit, so the thing doesn't propagate too much. Okay, so still there will be propagation a little bit, but not too much because of this freezing. So the freezing idea is also very crucial. It helps you avoid some propagations, error propagation in the sequential decoder, but nevertheless this is the crux of the idea. So how do you recreate bit channels at the receiver? You do sequential decoding. You decode one at a time, and you go in the sequence 1 to n, but wherever you have frozen positions, you use 0. Okay, that's the essential and crucial idea. Okay, so it's quite a simple idea at some level, but this picture is important to keep in mind. Okay, now to describe this SISO decoder, we need to use the binary tree representation, and we will start with n equals 2. Okay, n equals 2 is the simplest possible case. Maybe it's not a practical decoder at all. You will never use a code with n equals 2, but it's an important building block in the SISO decoder. Okay, so I'm going to describe what happens in n equals 2. Remember, n equals 2 is just a depth 1 binary tree. You have a root and then just 2 nodes, 0 and 1, and u1 is the bit that's input here, u2 is the bit that's input here, and then what you put out is u1 plus u2 and u2. Okay, so if you call this as x1 x2, u1 u2 is the input, you run it through the kernel g2, you get x1 x2, and x1 x2 is transmitted with BPSK AWGN. Remember, BPSK AWGN is 0 to plus 1, 1 to minus 1, and AWGN is noise added. You get R1 R2. Okay, the R1 corresponds to x1, R2 corresponds to x2. Okay, remember, when x1 was transmitted, R1 was obtained. When x2 was transmitted, R2 was obtained. The whole thing about the decoder is how do you recover u1 and u2, right? How do you get soft information for u1? How do you get soft information for u2? And how do you do the hard decision? That's it. That's the only point. And for that, it turns out our old ideas of single parity check and repetition are what is used again. Okay, so the only soft ingredients that we use these days is the single parity check code and the repetition code. Okay, so I'll tell you how that comes about. Okay, so if you look at x equals xn plus x2, you can write u1 in terms of x1 x2. Okay, so this is we write x in terms of u1 u2, the kernel going in this way. You can actually invert the kernel and go back in this direction. Okay, how do you do this? u1 is x1 plus x2 and u2 is x2, right? It's just a simple, so you XOR these two guys, you get u1. Okay, that's the idea. Okay, so it's easy to do, and you get u1 as x1 plus x2. Okay, so remember this, you get u1 as x1 plus x2, and then R1 was received when x1 was transmitted, and R2 was received when x2 was transmitted. So R1 and R2 is like a belief for x1. R2 is belief for x2. Okay, and what do you want? You want belief for u1. Okay, and what is u1? x1 plus x2. Okay, you have belief for x1, you have belief for x2. What is the belief for x1 plus x2? Okay, this is the classic single parity check problem, right? So this is the extrinsic information for single parity check, and for which we can use the min sum method. Okay, how do I use the min sum method? I'll take the sign of R1, multiply with the sign of R2, and then take the minimum of the two absolute values. Okay, you can also use the tan hyperbolic and log tan hyperbolic and get more accurate soft information if you like based on the XOR, but let's use min sum. Okay, so we've seen min sum is close enough, and this min sum function I will call as f. Okay, so note this notation, this min sum function I will call as f. F of R1 R2 is sine of R2 R1 sine of R2 multiplied by sine of R2 multiplied by minimum of the two absolute values. Okay, so this is something important, and note it down. Okay, and you can see that this is just single parity check code right there. Okay, so this is your belief for u1. I'll call it L of u1, and it's obtained using the min sum. Okay, Once you have a belief for u1, finding u1 hat is just a simple hard decision estimate. This is just a threshold. Okay, if the belief is positive, you say u1 hat is 0. If the belief is negative, you say u1 hat is 1. Okay, hopefully this is clear to you. So the SISO decoder for n equals 2 is quite simple. It's straightforward. It's a simple single parity check transformation. Okay, remember once again, we are not doing u1 and u2 together. Okay, so this SISO decoder for the polar code with n equals 2 is slightly different from maybe doing the overall decoding together. Okay, you decode u1 first, and once you find u1, you use the estimate of u1 to decode u2. Okay, you are not doing it jointly, you are not finding u1 and u2 jointly. Okay, you could find u1 and u2 jointly, that will be another decoder, but the polar decoder does not work like that. It works with successive cancellation always. Okay, so this is more like a successive cancellation SISO decoder. It is not really the sort of optimal SISO decoder from other areas. Okay, so this is a successive cancellation SISO decoder. Okay, so once you know u1 hat, notice what happens. Okay, if u1 hat is 0, okay, your x is u2. This is actually repetition. Okay, all right, think about it. So if your u1 hat is 0, then your x simply became repetition. Okay, right. So what is the meaning of repetition? So what you sent was actually u2. So r1 is also a belief for u2. R2 is also a belief for u2, okay, because u1 hat you have identified as 0. You assume once you find u1 hat, you assume that u1 is 0. Okay, that is the nature of successive cancellation decoding. You figure out u1 and then use it, assume it's true, and find the next one. Okay, once u1 you know is 0, it's actually a repetition code. X is just u2. So r1 is a belief for u1, r1 is a belief for u2, r2 is another belief for the same u2. Now when you have repetition code, you simply add the beliefs. Okay. Now if u1 is 1, actually the situation is very similar. What is x? It's u2 bar, which is the complement of u2, right, 1 plus u2 and u2. Okay. So r1 is a belief for u2 bar, the complement of u2. So if you have a belief for the complement, what is the belief for the actual bit u2? Minus r1. Okay. So if you think about it, see, BPSK is 0 going to plus 1, 1 going to minus 1. If for a particular bit you have a belief, its complement, the belief is negative, right, the minus of that. Okay. So when u1 hat is 1, what you transmitted is u2 complement and u2. r1 is a belief for u2 complement. So minus r1 is another belief for u2. Okay. Similarly, r2 is a belief for u2. Okay. So what is the total belief? r2 minus r1. Okay, which is actually again an addition, except that because of this complement you have to do r2 minus r1. Okay. So once again I want to emphasize what's going on here. Let me repeat from the top what's going on. The basic building block for the polar decoder is a successive cancellation SISO decoder for this simple n equals 2 situation, and for that the essential components are once again the single parity check and the repetition. Okay. The single parity check is sort of obvious, only the extrinsic matters, and it comes down from just u1 being x1 plus x2. Okay. So you use the min sum to find its belief, and for the repetition there is this little twist because of the successive cancellation. Okay. So if the previous bit was 0, it's a pure repetition, so you just add r2 plus r1 because both received values are beliefs for the same bit u2. On the other hand, if u1 hat is 1, then there is a complement involved. So you have to multiply one of the beliefs by minus 1 and add. Okay, so you do that, you get the belief for the next one. Okay, so this is the crux of the polar decoder, the simple block that you have here, and this is how you decode on the tree. Okay, so I'm going to in the next slide interpret these steps as message passing decoding on the tree. Okay, so once we see it as message passing, you can start extending it to larger block lengths and see how the message passing can be extended to larger block lengths. Okay, so let me show this as message passing on a tree. Okay, so this is what happens for the basic building block message passing for a tree. Okay, u1, u2 are the message bits, this is the code word bit, and this is the belief or the channel received value. Once again, I keep saying belief People use log likelihood ratios, but we are going to be slightly more generic there. Usually we use the received values directly as beliefs. Okay. Now that obviously that happens in BPSK AWG, and if your modulation is different, you have to compute the belief per bit using some method and then use this algorithm. Okay. So what is the first step? This is step 1, this is step 2, this is step 3. What is the first step? You have R1, R2, the belief for x1 and x2. You send f of R1, R2 from the root node to the leaf node on the left. Okay, so this is very important. This direction, whether it's on the left or right, is very important. Left comes first. Okay, you always go left and below first. Okay, so that's the rule to remember. Okay, and this is the min sum function f of R1, R2. Okay, so you compute that and send it out. Okay, in the second step, the leaf node figures out what u1 hat is and sends it back to the root node. Okay, so that is just a hard decision. Okay, so this is a hard decision on f of R2. So notice the belief we had for u1 at this point we are not using. Later on in when we study the list decoder, we will use that belief. Okay, so right now the belief for u1 is not used. It's a soft output that's available. It's just merely merely do a hard decision decoding. Okay, so now once you have u1 hat, okay, what goes the next step? In the next step, after you have u1 hat, from the root node, you will send a message to the right child. Okay, so in the first step, you sent a message to the left child, and then you got something back from the child. Okay, so this is very important. You send a message to the left child. Okay, and then you wait for something to come back, the decision to come back from the child. Okay, once you get that decision, you send a message to the right child. Okay, the child on the right. Okay, so once you have that, you send a message to the child on the right, and what is that message? That's where the repetition code comes in. I'm going to use this function g. Okay, so this is a bit, okay, 0 or a 1. This function g succinctly captures the complement situation. Okay, if b is 0, you have R2 plus R1. Okay, b is 0, you have R2 plus R1, and if b is 1, you have R2 minus R1. Okay, so this is just a shorthand notation to capture this the complement situation that you have here. So what you send here is g of R1, R2, u1 hat. Notice the little switch here. I'm calling it R1 comma R2, but I do R2 plus 1 minus 2b R1. Okay, something to pay attention to. Okay, so once you have this, that's the second step. You sent a message to your right child. Okay, this g function was involved in that, and then you do a hard decision. Okay, so once again at this point we ignore the belief for u2, we simply do the hard decision. I mean, we don't ignore it, and we do the hard decision and throw it out, but later on in the list decoder we will make explicit use of the belief for u2 as well. Okay, so now once the root node has heard decisions from both the children, okay, so here is a decision from the first child, here is the decision from the second child, both the leaf nodes or both the children have given a decision back, the root node can now decide. Okay, what will it decide? u1 hat plus u2 hat, u2 hat. This is the code word which goes up from the estimated code word which goes up from the root node. Okay, I want to point out a couple of things here. My message is in u1 hat and u2 hat. I really don't need the code word, right? What do I do with the code word? Message is u1 hat and u2 hat. Once I find u1 hat and u2 hat, I am done. Okay, I really maybe don't need this. X hat is this. Okay, so this, as it turns out, is needed for larger n. Okay, so this kind of a flow is needed. You will see the next slide I will start describing n equals 4. For n equals 4, sending a message from this node is also important. Okay, so what it sends up will also play a role, and that we will see when we look at n equals 4. Okay, so this part strictly, if you are just decoding n equals 2, you don't need to go back and construct this x hat. You can just happy with u1, you be happy with u1 hat and u2 hat, you are done with that, but you need this x hat for when you use this as a building block, when you use this as a building block for larger larger block length, you need this x hat also. Okay, so this is the n equals 2 building block. Hopefully this was clear. The next step is how do you use this as a building block in n equals 4. Okay, we are going to go to that in the next slide. Okay, so now how is the situation for n equals 4? If you remember, the binary tree is slightly larger you have depth 2 in the binary tree. Okay. So, the root node is here, and then you have depth 1 nodes, and then you have depth 2 nodes, right. So, that is the nodes in the binary tree, and you have u1, u2, u3, u4. You find an intermediate vector v1, I am going to call it v1. This is u1 plus u2, u2, and v2 is what? v2 is again u3 plus u4, u4, right. This is v2. So, notice this is 2 bits. Okay. Now, this v1 and v2 are, remember, 2 bits long. These are vectors of 2 bits, and these are combined again to find the code word x. x1, x2 is v1 plus v2, v2. Okay, you can write it back in terms of u, but v1 plus v2, v2 is pretty nice. It's just 2 bits each though. So, this is 2 bits, 2 bits. So, it becomes 4 bits. Okay, overall you have 4 bits here. So, this is the idea. We also saw the program for writing this encoder. So, this is how the whole thing works. Okay, this is the code. u1, u2, u3, u4 is what you originally have, and then you go to x1, x2, x3, x4 after this operation with G4, and then BPSK AWG, and as before 0 going to plus 1, 1 going to minus 1, then noise getting added, you get R1, R2, R3, R4. Remember again, R1, R2, R3, R4 are beliefs for x1, x2, x3, x4. How do you find beliefs for? Beliefs for u1, u2, u3, u4 is the central question that we answer in the successive cancellation decoder, the polar decoder that we have. We do it in a successive fashion. We first find the belief for u1, then use the decision on u1 to find the belief for u2, and then use the decisions on u1, u2 to find the belief on u3, and then you find the decisions, use the decisions on u1, u2, u3 to find the belief for u4. Okay, so that's how we'll proceed, and we'll go along the tree. You'll see we'll go along the tree in a certain way, just much like before, and I'll describe that in the next slide. Okay, so the tree plays a very crucial role. Okay, so this is the first step I'm showing here. This is step 1. Okay, so this is step 2. Remember again, we got R equals R1, R2, X1, X2. Remember, X1 is 2 bits, X2 is also 2 bits. Okay, so that's how I've written it up. X1 is 2 bits, X2 is 2 bits. So this R1, R2 is belief for, so let me be careful here. So there's some ambiguity in the notation. Notice this is, I've also written X1, X2, X3, X4 here. Remember this, this is not X1, X2. So I should write this as X11, X12 and X21, X22. Okay, so this is better notation. We'll go back and correct it. So I have X11, X12, X21, X22. This is the first bit of X1, second bit of X1, first bit of X2, second bit of X2. Okay, so X1 and X2 are 2 bits each. These are beliefs for X1. Okay, the R1 is the belief for the first bit of X1, R2 is the belief for the second bit of X1. Likewise, this guy is belief for X2. Okay, remember that. Okay, let me write this step 1 here a little bit off this side, and then I can say this is beliefs for X2. Okay, so the vector together R1 and R2 is a belief for X1, the entire vector X1, X11 and X12. Okay, so now remember, once you have X, what is V1? V1 is X1 plus X2. Okay, you can go back to the previous thing and see X is X1, X2, V1 plus V2, V2, and V1 is actually X1 plus X2. Okay, so that's something important to know. Okay, so V1 is X1 plus X2. Okay, so you have beliefs for X1, you have beliefs for X2. What is the belief for X1 plus X2? You use min sum again. Okay, how do you use min sum? You use min sum on R1, R3. Okay, so because why do you use min sum on R1, R3? This is belief for X11, this is belief for X21, this is belief for X12, this is belief for X22. Okay, and V11, the first bit of V1 is actually X11 XOR X21, right? Isn't it? This is what? This is X11 plus X21, and then X12 plus X22. Okay, so X11 plus X22, X21, how do you find the belief for that? You do the min sum f of R1, R3. Okay, R1, R3. Then X12 plus X22, how do you do the belief for that? F of R2, R4. Okay, so that's it. So simple single parity check code soft output decoding, and that's the beliefs you send down below. Okay, so you have 2 bits here for V1 and I've got beliefs for both of them. Okay, all right. So once again, you had 4 bits at the code word, you got 4 received values, 4 beliefs, you grouped them 2 at a time and then computed the 2 beliefs for V1. Okay, and now once you have beliefs for V1, this is just a vector of length 2, you're back to the n equals 2 situation, right? At this point, you're at the n equals 2 situation. Okay, what happened at n equals 2? You had a root node and you had 2 beliefs coming in. Same thing is happening here. You have a root node and you have 2 beliefs coming in and you have 2 leaves below that. Okay, and step 2 is just n equals 2 decoding. Okay, so that's the basic building block. Okay, what do? You have 2 beliefs coming in. Remember, you have the 2 beliefs L equals L1, L2. Maybe I should write that down somewhere here. L1, L2 are coming in here. Okay, so that's the L that you had here, f of R1, R3, f of R2, R4. L1, L2 is coming here. And what do you do in the n equals 2 decoding? We know what to do. You do the min sum function, f of L1, L2 goes down, U1 hat comes back in, g of L1, L2, U1 hat goes down to the right side, and then U2 hat comes back in, and what goes back up? U1 hat plus U2 hat, and then U2 hat. Okay, so I was mentioning how this code word going up is important. Okay, so this goes up to the root node. Okay, so now we have to figure out what the root node is going to do. Okay, so the root node sent some belief down to its left child. Okay, and now it's getting decisions back from the left child. Okay, so remember this operation once again. The root node got some beliefs from the top. Okay, it did some minor processing with this f and sent beliefs down to its left child. Okay, and it has now got back decisions from its left child. Okay, now the root node will have to send something to its right child. Okay, which is what is going to happen in the next step. How do we do that? Just like we use the function f, we'll use the function g now. But when you use the function g, remember there are 2 bits now. You have to send a vector of 2. So what do? That's the next step. Okay, so this is step 3. Okay, so you got these decisions from the previous step, right? So from previous step, from step 2, we got these 2. The decisions from the left child are coming back up. Okay, now what are the beliefs you compute here? You use g. Okay, just like before, except that you're going to use g on the 2 bits, right? So you have x1, x2 here. You look at what happens here. So once again, x11, x12, x21, x22, and then you have r1, r2, r3, r4. You look at r1 and r3 and x11 and x21. Okay, so if you look at just those 2 bits, okay, they make a repetition code. Okay, just like before, and everything depends on the decision u1 hat plus u2 hat. If u1 hat plus u2 hat is 0, it's a pure repetition code. You can simply add the beliefs r1 plus r3. But if u1 hat plus u2 hat is 1, you have to do the complement, so the belief will become r3 minus r1. So that's why you do g of r1 r3 u1 hat plus u2 hat. That's the repetition. Okay, so it's like a repetition. Okay, so likewise these 2 guys are also like a repetition. Okay, so you do g of r2 r4 u2 hat, and u2 hat is your decisions to guide that repetition. Okay, so you use once again this function g, except you group your bits as repeating blocks 2 at a time, and then use the same function g and the decision that you got from the left child to guide what to compute as beliefs for the right child. Okay, so this is L equals L1, L2 beliefs going down to the right child, and this part is now n equals 2 decoding. And that's what I'm doing here. Okay, f of L1, L2 goes down below to the left child, u3 hat is a decision that comes back up, g of L1, L2 u3 hat goes down to the right child, u4 hat is the decision that comes up. Okay, that's L2 decoding. And once u3 and u3 hat, u4 hat have come back up to this node, it sends back v2 hat, which is u3 hat plus u4 hat, and then v1 hat was anyway there, u1 hat plus u2 hat, and then you can find a x hat, which is v1 hat plus v2 hat. Okay, So, now once again, once you find u1 hat, u2 hat, u3 hat, u4 hat, you are done as far as n equals 4 decoding is concerned. Okay, you do not need anything more. Okay, but we are going to proceed and look at this calculation of the code word also. This is the estimate of the code word, and you do not really need estimate of the code word for decoding n equals 4, but why will I need estimate of the code word here? When I want to go for larger n. Okay, so this is useful for larger n once again. Okay. So, this is the essential working of the polar successive cancellation decoder, soft input, soft output actually, but we do hard decisions as we saw. It is sequential, it decodes one bit and then uses that decision to go through and decode another, and it uses very basic simple building blocks, just 2 bits single parity check code, XOR of 2 bits together, okay, just min sum with 2 inputs and 2 bits repetition. Okay, just repeating twice, and even for larger block length you group the bits and identify the 2 bit repetitions and you are using it. Okay, nothing more happens on the polar decoder. It is very simple steps, and the sequence in which they are combined together is the beauty in it, and that is where the performance comes in. Okay, so I am going to stop here for this lecture to explain the philosophy and the way in which the decoder works, and in the next lecture I will start generalizing. So, you see what the node does. The node receives beliefs from the top, sends some beliefs to its left child, gets back decisions, sends some beliefs to the right child, gets back decisions, combines the decision and sends it back up. Okay. So, this is what every node does on the tree. Okay. So, once we describe what every node does, we can describe the entire decoding algorithm for any n. Okay. So far I showed you only for n equals 4, we will generalize from here and talk about how the decoder works for a general n, and that I will do in the next lecture. Once we are done with that, we can write a simple MATLAB code to simulate it, and we will be done with the single successive cancellation decoder for polar codes. Thank you very much.